Hello everyone, and welcome. Welcome to this session. Let's wait for a couple of minutes while everybody joins. Hello Milo,
Hi,
how are you?
fine.
Very good.
Thank you.
Great. So before everybody joins, maybe we can spend a couple of words. So for the ones that have joined already, welcome again. And it's a pleasure to host you in this seminar that is hosted by myself and Milo from Newtwin. My role in Newton is the head of business development, so I am covering the commercial activities like partnership, marketing, and so on. And I will be having the presentation today with my colleague Milo, who is the CTO of the company that will be taking the word later on. The idea today is to have conversation, an overview of the virtual thermal sensing technology, or we like to call it VTS technology, that is rapidly raising technology across specifically the automotive sector. Maybe I can start sharing the screen while some people are joining. Welcome again to everyone who is joining now. There we go. Okay. There we go. Perfect. So you should be able to see my screen now. Amazing. I can see that more and more people are joining. Welcome again. As we were discussing before, the conversation today will be on virtual thermal sensing technology, and we are going to be seeing an overview of the market, and then we will focus on the methodology and how this technology is being brought to the market. Now, I would say that we can officially kick off. The agenda of today is this one that you can see in the screen. We will be starting with the challenges that we are currently seeing in the thermal management space, and specifically in those high power density components. Challenges that we are seeing a lot in the automotive segment, in components like traction inverters, onboard chargers, eMachines, and so on. We will move to seeing what is the blind spot that we are seeing in this e-powertrain space. We will see the limitations on the current technology that we are seeing in the market, to move then on what a virtual thermal sensor is, some use cases from existing customers that we have been working with in the past years, to then move on the methodology, how a virtual thermal sensor is built and deployed for this kind of components, to then finish with the tools, the platform that is being used. Please, during the presentation, if you have any questions, feel free absolutely to drop them. You have a DNR button up in the screen, as you can see. So if something comes up, please write them down. So we will be happy to cover them at the end of presentation, where we have reserved some time to answer all the questions. Great. So as I was mentioning, we have noticed that Electrification systems are rising in complexity. Electrification systems like high power density components. And these components are rising across several industries like e-mobility, industrial, space tech, marine, and so on. And since these applications, these industries are seeing a rising demand for these kind of technologies, also, there is an highlight on the limitation that the current sensing technologies have. Traditional sensors are simply not enough to satisfy the requirements that these kind of complex components have. And today we are going to be focusing on the thermal aspects. We're going to be seeing why the thermal management of e-powertrain components is crucial for, let's say, performance and safety reasons. Now, why is thermal management a problem today? Is a problem because nowadays there is a blind spot. We have seen across many applications that the critical hotspots of the e-powertrain components is just simply not measurable, and temperature in these components is a critical state variable. So we, of course, deep dive on what was the, let's say, state of the art, and across several customers, we asked what was, how was temperature calculated in real time for derating strategies. How was the temperature controlled to make sure that the system could operate at best. And we found out across many industry players that the state of the art today is that temperature is monitored by physical sensors like NTCs. But for example, the critical hotspot of a traction inverter, as you probably all know, is the junction that, of course, the NTCs cannot be placed in the junction. So we have seen that on top, let's say, of the correlation between the actual temperature in the junction and the temperature that was recorded by the NTC, it was necessary to put a calculative safety margin. Safety margin that we have seen raising up to 30, 40, sometimes even 50%. Here in the picture, in the slide, we can see a practical case of a traction inverter, and that we have been working with a customer, and the sensor was placed here, where you see that temperature was recorded at 70 degrees, while of course the hotspot of the die in the junction was recorded at 200 degrees. So a very high, let's say, discrepancy between the two temperatures. Then another, let's say, limitation of physical sensor is the fact that they are recording just one point of the component, like this case with any machine, while the temperature dynamics, of course, they are different. So while potentially you're recording a specific temperature, it might not be the highest, and you are not aware of the temperature distribution of the overall system. So, since there are some limitation, let's say, with physical sensors in the market, there is rising technologies that are software solutions. But these technologies, we have also seen that cannot really substitute physical sensor yet. Why not? Because they cannot guarantee enough across because they are not able to guarantee reliability across all the operating conditions. So, for example, where the flow rate changes, then these technologies are not scalable across different components. They are very system specific. So potentially you might be using a thermal network for a traction inverter, but that same technology, that same model cannot, of course, be used for a different component that the company is producing, like any machine. And then again, in compliance, they might not meet the stringent requirements that we are seeing, especially in the automotive sector. So, as I mentioned, companies, nowadays with software solution, they are relying on technologies like thermal networks or AI/ML models. But these solutions, of course, they have stringent limitations. In fact, for example, the main blockers that we have seen by working with customers is that usually there is an accuracy or computational trade-off. They might not be accurate enough, or if they're accurate, they might be too heavy in terms of computational requirements, and therefore they cannot be put in the microcontroller unit of the component to run in real time, which eventually is the goal of the virtual thermal sensing technology. Then another blocker is that for calibration, they require an high amount of data. So this, of course, impacts the development time. And again, as I mentioned before, they are very system specific. So, for example, there might be thermal networks expert in traction inverters, but then it would be difficult to replicate that technology and model across other components. Then, so to summarize, current sensing technology, both physical and software, they have limitations. These limitations bring engineers to put cautelative safety margins, and these cautelative safety margins are hindering strongly the design efforts that eventually are going to impact negatively the performance, safety, and cost opportunities of the components. This is where NewTwin and the virtual thermal sensing comes into place. We acknowledged that companies were encountering these limitations. They were encountering these kind of problems when it came to thermal management. So we are bringing to the market the virtual thermal sensing technology, and we are bringing it with a unified platform. But what is it? What is the virtual thermal sensing technology? It's a software solution, and it has the benefits of, let's say, any other software solution that potentially has no sensing placement limitation, and on top, it also has the benefits of, let's say, more physical sensor, because it can guarantee a level of accuracy across many all the spectrums of the operating conditions. So with these two benefits, of course, you can already acknowledge the fact that virtual thermal sensing is a strong added value compared to physical sensors or other software solution. The let's say main benefit, of course, is that potentially it can replicate, sorry, not replicate, but complement physical sensors, but it can even potentially replace them. Now, as I mentioned before, the benefit of having this kind of technology embedded in real time in the microcontroller unit is that it can allow you to reduce the cautelative safety margin that we are seeing in the automotive industry, but not only. And at the same time, you can increase the safety of the system, along, of course, with the performances. Now, why choosing VTS across other technologies? The reasons are related to the points that we have seen before. So you can reach a level of accuracy of plus minus 3 degrees. We have seen in specific cases reaching even better results, even 2 plus minus 2. Then it is reliable across all the operating conditions. Then another benefit is that potentially you could scale this technology with the exact same methodology across any other component. You would just need the inputs and you would gather the same output, let's say, to embed in the microcontroller unit of the component. And also, the output of this of the model is automotive compliant. Now, as I mentioned, we worked with many customers and we applied the technology to many different components. The ones that you are seeing here are real cases that have applied successfully the technology, but potentially the VTS could be applied to any e-system component. And for example, the critical hotspot that we were mentioning at the beginning in any machine could be the head winding, the rotor magnet, or the bearing shaft. Critical points that eventually are not estimated or measured correctly with what we are seeing today in the market. When it comes to traction inverter, critical point to be monitored that today is just not possible to monitor is the junction temperature of the power module. And again, for the onboard charger, we have similar hotspots that we are seeing as critical to monitor. So what I shared now is a general overview of what we have seen as challenges in the market and the potential benefits that this technology can bring. And now I would like to pass the floor to Milo, so he will deep dive specifically in the technology and in the methodology that has been used to bring VTSs on the edge.
Thank you very much, Andrea, for the introduction. And let me share my screen. And you should be able, see, 1 second. You should be able to see the presentation. So I will, in the rest of the time of this presentation, I will provide you an overview. We would need several hours actually to deep dive in any technicality, in all the technicalities behind the construction of the virtual thermal sensors, but I will try to convince you in a few minutes that compared to the state of the art, so if we imagine the process of building and calibrating thermal networks, that this kind of methodology can be much more beneficial, especially in terms of capability to scale this methodology across multiple components, and also giving access to this knowledge and to this tool to multiple engineers inside a team, inside a company, and without requiring deep expertise on the mathematics behind. So let's start by giving you an idea which are the steps for creating successfully virtual thermal sensor. So here you can see all these phases that are required to arrive to the final product, which is actually a piece of software that can be integrated in the embedded environment. Compared to other methods, as we said, thermal networks, for example, but also other approaches like fully data-driven approaches that we have seen in the industry out there, we do not discard classical physics-based numerical approaches that typically are employed by engineers across all the industries, and therefore our starting line is a full order model derived from an available CAD drawing combined with the well-known finite element analysis. And this is typically a very good starting point. First, because it is accessible. It's something that is always available in a development team, development engineering team. And it has already a lot of knowledge from the engineering field, engineering domain that can be used to prepare a digital model. Of course, as you all know, a full order model, as we call, would be impractical to use in a real-time embedded application as a virtual sensor in this case. And therefore, the second step and the first actually jump into the virtual sensing is actually the reduction phase. So the possibility to create a reduced order model starting from the full order one. And this is an essential step because it basically reduces the complexity of the numerical model while holding the same accuracy. So given that the engineer has designed accurately a full order model, we provide a simplified version of this model by holding the same accuracy. And then we come to the most crucial and important phase, which is actually the calibration. So a virtual thermal sensor cannot be produced if we are not able to calibrate it. In fact, inherently, any kind of simulation model has some sort of simplification compared to the reality. This is, of course, necessary in order to represent it with the computational power that we have in our machine. So we cannot actually simulate all the details of the real world, and therefore a full order model and a reduced order model by design, they would not be accurate and reliable enough to be deployed and used in a real-time application. And by having the possibility of calibrating the physical parameters encoded in the model, then we are able to actually prepare the model for working in the field. So to be able to estimate the real behavior that we can then later on experience while the component has been manufactured and put in operation. Once the reduced order model has been calibrated, we could say that the physics-based part is ready, and actually we have a lightweight model that can be used in the field. Optionally, there is also the possibility to add what we call discrepancy model. So as you may know, AI has gained momentum over the last few years, and in particular, its application in the context of the scientific modeling, it is actually trending. And it can be actually used independently or alternatively to physics-based approaches, but more interestingly, the data-driven algorithms can be combined in a complementary way, making the whole simulation architect very effective in tackling real-world application, especially where we have challenging nonlinear phenomena that can affect the output of the system, so that can affect the temperature behavior of the component. And therefore, what we call discrepancy modeling here, it is a key and effective tool for enhancing the real-time capabilities of the virtual thermal sensor and offering a real-time correction of the physics-based estimation. We can see later what we are talking about. And finally, the last steps, once the digital model is ready, is the preparation and the optimization of the source code and the source application that can be then embedded into the real-time application. So as we have said, the starting point is the finite element model constructed upon the mechanical CAD available. And as you can think, actually, this by nature gives us the result of the finite element method approach applied on a 3D solid actually naturally produces a mesh geometry, which is actually a fully connected 3D very accurate thermal network. So by nature, we already have what we want, and we also have the flexibility by controlling the grade of the mesh to decide how granular we want our resolution to be. And this can be helpful later for placing virtual sensor in the spot where we are interested in monitoring the temperature. Model order reduction. Well, so in literature, there are multiple techniques available. For example, we can talk about balance truncation, moment matching, and of course, these kind of mathematical techniques, they are not just taking the full order model representation and simplifying the original mesh behind, so simplifying the degree of freedom by removing node of the mesh. The model order reduction reduces computational complexity without modifying the original full order model. In fact, it finds a low dimensional representation of the thermal system, identifying the dominant characteristics. It is an iterative procedure in which actually the full order model is tested in the parameter space. So parameters are sampled inside the parameter space. The full order model is tested against them. And then based on the response of the full order model, a low rank, so-called low rank base is constructed iteratively so that we end up having the same exact initial problem provided by the finite element approach, but with a very small set of linear equation. Of course, the reduction procedure provides also the so-called projection matrix, which is actually the key in order to reconstruct with very high accuracy the temperature in any area of the original full order model. So in the end, we have a very lightweight, a very small set of equations that we can solve very quickly and obtain the resulting temperature in any node of the original mesh that we have designed during the physics setup of the full order model. And then we step into the calibration phase. So as we have said, simulated systems inherently deviate from real physical system due to complex effects that might not be modeled. And therefore, as a result, unlocking the possibility to calibrate the model is crucial. Calibrating the model is basically, it means to solve the inverse problem. I have a set of parameters that describe my reduced order model, or my full order model actually describes the thermal physics. And on the other side, I have, for example, a prototype that has been manufactured and tested on the test bench. So I have some response of the real system. And the calibration finds try to adjust the parameters, adjusting the values according to their uncertainty in order to fit the final response that we have measured on the test bench. And in this scenario, the reduced order model availability plays a very important role. In fact, it would require a huge amount of time to execute thousands of transient simulation to find the best parameter set if we would have only the full order model at disposal, which actually typically is a model that have millions of degrees of freedom, which are based on the node of the mesh. But thanks to the reduced order model obtained in the previous step, we can do it very effectively and obtain a final calibrated digital model, which is suitable for real-time estimation. As I have briefly told before, applying machine learning in this context, it ends up being very effective. In fact, you can think that on one side, we can leverage the machine learning to uncover complex nonlinear patterns in the data, which may be very expensive to encode in the classical physics-based model part. And on the other side, we can exploit domain knowledge provided by the physical model that we have constructed by the model order reduction and calibration to avoid overfitting during the training of a machine learning model. For example, in this context, we are talking about neural networks, and also to contain the size of the resulting neural network. which is beneficial for the microcontroller memory usage in the final application. We need to say that in this context, naive implementation of classical artificial neural network architectures, it is typically very limited. It is not enough because we need to guarantee certain properties for this kind of machine learning discrepancy model to be suitable for the purpose of building a virtual thermal sensor. For example, since the digital application, the digital model will be working in real time, we need to guarantee stability of the discrepancy model in order to avoid that if something happens in the input data, the correction provided by the discrepancy model to the physics-based estimation is not drifting towards values that are completely not plausible, and then would end up providing an estimation that is not reliable anymore. And also, this kind of this machine learning architecture must be lightweight, as we have said, because they need to be used in real time in a very low power microcontrollers. And they also need a limited amount of data for being trained because, of course, generating test bench campaign, measurement campaign is also expensive. And then here in this slide, you can actually see the final architecture to expect from a virtual thermal sensor. So following the procedure that we have described, the architecture of the software, it is composed like that. Typically, we have a loss model. So piece of software that is describing how the heat is generated inside the device. And this is typically coming from the domain knowledge. So engineers that have designed the component know exactly how to describe the loss generation starting from the available input. For example, the current, the frequency, the speed, if it is a rotating machine. Then we have the cooling model, also how the heat is extracted from the system. For example, it can be a very simple model, but in certain situation, we might have forced cool system, water cool system, oil cool system, and or maybe we might have some fan that can have different speed. And therefore, we can also encode in the virtual thermal sensor these informations. We have, of course, the core of the VTS, which is actually the thermal model, where the physical simulation happens in real time. And the discrepancy model, as I have described before, is an optional tool that can be integrated inside the architecture when we are trying to build VTS for a challenging application where there are uncertainties in real time. So typically variables that we cannot control directly, we cannot measure, boundary condition that can change, temperature that can change around, flow rate that can change, and so on and so forth. Discrepancy model has the task to map these kind of uncertainties and react to correct the estimation in real time, guaranteeing that the temperature that we estimate where we have placed the virtual sensor is always accurate in all the operation of the system that we are designing. And finally, here we have an application slide. It's quite dense of information. I will try to condense them in a few minutes. So first of all, in the middle, you have actually a datasheet of what to expect in terms of resources. So virtual thermal sensor is a piece of software and that can run in a low power microcontroller, has been designed for this purpose. And there you have an example of the resources and the performance that you might expect on hardware. In this case, we have here some data related to an Infineon Aurix TC3. But averagely, the memory consumption and the execution time that we see here can be taken as a reference. And then we have two very interesting use cases. On the left, we have the simulation of a three-phase traction inverter. Focusing on the inverter application, the scope there. So we could design, of course, a virtual thermal sensor for monitoring the junction temperature of the power module on board, because typically that is the main variable of interest that we would like to control in real time. And therefore overcoming the limitation of the NTC, which is always present, but it is not enough in order to estimate correctly what is the temperature on the hotspot on the die, on the junction die. What happens is that if we design a virtual thermal sensor for the traction inverter application, we can use that information in the control loop in order to derate the power based on the precise information on the junction temperature in real time. So in the example there, we have actually some current that is impressed. So the maximum current can be impressed, and then the junction temperature can be monitored. And as soon as the junction temperature reaches the limit temperature based on the power module data sheet, power derating can happen in two ways. One way is to reduce the frequency as much as it is possible. And then when frequency is reduced to the minimum available, then also the amplitude of the current can be reduced. And this can guarantee that the maximum current can always be impressed by respecting the limit temperature of the junction. There is also another interesting fact. By having the real-time information about the junction temperature, it is also possible to leverage on this information to exploit the TLO, what is actually the time-limited overrating. In fact, manufacturer of chips, so supplier of the semiconductor industry, they have this kind of indicator, which is actually an indicator that allows the application to be operated over the limit temperature. The power module can be operated over the limit temperature for a certain amount of time without incurring in a hard fault of the power module. But aging can happen, of course, during this. And exploiting this, the information of the junction, it is also possible to exceed for a limited amount of time the maximum temperature, providing the maximum performance, the maximum current that can be then delivered to the electric motor. On the right side, instead, we have the case of the electric motor, exactly, so the complementary component to the traction inverter. Regarding the electric motor, we would typically design virtual thermal sensor for controlling and monitoring in real time mainly two variables. One is the temperature in the winding in order to protect the insulation layer in the windings from overheating. And this can be seen from the plot on the top. And of course, we can design and place virtual thermal sensor in the hotspot, or we could also leverage on multiple virtual thermal sensor and then use this information for introducing in the control loop the real-time estimated temperature of the winding in order to derate the power according to the level, to the value of the temperature in real time. This can help a lot, also mitigating the limitation of the NTC, which typically there are challenging especially during the manufacturing process in actually connecting precisely an NTC on the winding head, and therefore we could think about having a complementary application in which the NTC sensor can be placed in a safe place, and also leveraging on the virtual thermal sensor to, in any case, having a precise information on the winding temperature in real time. And then on the bottom, we have actually the rotor temperature monitoring, which is also the other very important information that we would like to have in real time, especially when we are talking about permanent magnet electrical machines, where we need to avoid the demagnetization area. At the state of the art, actually, it's infeasible to have sensor temperature placed physically in the rotor. Therefore, without any kind of software tool, it would be impossible to know the temperature in the rotor. And virtual thermal sensor in this case are very effective, especially because the rotor has the problem that during on-off cycle, if we are imagining a driving cycle, they heat very slowly and they also cool down very slowly. Therefore, after several on-off cycles, we don't know where the rotor temperature is ended up, and then we could actually risk to overheat the rotor over time. The benefit of having a virtual thermal sensor in this case, since it encodes inside the software architecture a digital model, it is always possible during on-off time to actually, when the application start up again, by knowing that the time that is passed from the last on time, always possible to estimate accurately where the rotor temperature is, and therefore we can expect to have a robust monitoring of the rotor temperature over time during a driving cycle. And this allows us also to use the information of the rotor temperature in the control loop to optimize the thermal management. And in terms of control, if we cannot predict the forward temperature of the magnet using a reliable virtual temperature sensor, and achieving stable derating to maintain safe temperature levels for both the stator and the rotor would be basically impossible. And this highlights the fundamental importance of virtual temperature sensor in maximizing both peak torque duration and the continuous power output achievable by the electrical machine. Okay, so we arrived till the end, and I hope I gave you a good overview on the steps required for building effectively a virtual thermal sensor. Of course, many of you might recognize the complexity of the process and the multiple skills required, which traverse different engineering domains, such as finite element modeling, numerical simulation, optimization algorithms, data processing, machine learning, and embedded control system. We at Newtwin have recognized this problem early, and we have packed the entire workflow into a single software platform, which allow the user to progress and complete all the steps without having deep expertise in any of the various subjects and without writing a line of code. If this has, of course, aroused your interest, we will be happy to show you software in a practical implementation demo. And we also offer trial eventually. Thank you for your attention. I am also finished.
Thank you, Milo, and thank you everyone for your participation. Again, if you have any specific points that you would like to ask, feel free to drop in the Q&A settings. There is a question already.
Okay, thank you for your question first. It's very interesting. So first point is asking if we have experience with electric motors that are oil-cooled. The answer is yes. We have worked already a few cases, since we have also seen that actually this kind of cooling typology is spread in the automotive field. And we have successfully designed virtual thermal sensor for oil sprayed, double phase oil sprayed electric motor. Actually winding head that had spray cooling, and also the rotor was sprayed with a centrifugal force from the shaft. And yes, basically, as I have said, we have all the tools in our platform for tackling also such challenging scenario, where you also can avoid complex CFD simulation, for example. And we would be happy also to show this, how it is. And we have experimental result as well to prove that the accuracy can be obtained also in such complex scenarios where temperature of the oil can be unknown. The flow rate of the oil and the pressure of the oil can also be unknown. Of course, with enough test bench measurement, it is possible to design a virtual thermal sensor that covers all the operations in a very reliable way. We are working with several OEM. Actually, we are working with tier one, so supplier of component in the automotive. And we are working toward production with some of them, yes. Of course, it is a process that requires multiple stage of prototyping, iteration, especially as you can imagine. So the interaction on the supply chain is complex between tier one and OEM, and therefore the process is, it requires some time also from the tier one itself. Regarding the accuracy, that Andrea have stated before, the ±3 Kelvin. Actually, it is not only in steady state, it is both steady state and transient. In our software, we platform that we have briefly shown, so the Twin Fabrica, we offer all the tools in order to design and assess the accuracy, both in steady state and transient. Of course, you need to have the possibility to validate, so to make measurement, to record measurement on the test bench that are in transient. This kind of measurement can be used both for calibrating the virtual sensor and also validating it. And we have done it in multiple cases, and therefore we are capable to state that we can achieve such accuracy. And finally, the last question is regarding the time required for building and designing a virtual thermal sensor. This is actually depending from the availability of the input data, as you might guess. So I could say that if a CAD drawing is available, even better if an FEM model is available, which is actually something that can be imported directly in the software. And also a prototype with measurement is already available, and some measurement has been already conducted on the test bench. It is a matter of hours, I would say, or days, not more of that. Of course, typically some data need a few days to be collected, especially because since these data are distributed across multiple teams, and then they have different persons that are responsible of this data, sometimes some delay are just created by this communication of data. But once everything is available and everything can be imported in the platform that is unifying all the information from physics to calibration to measurement to test bench, etc., then it's really a matter of hours and days for building and validating the virtual thermal sensor. And thank you. Yeah, they were very good questions.
Thank you, Emilio. Thank you, Gianfilippo. I don't know if any other of the participants have any question. We have a few minutes left, so feel absolutely free to drop them here in the chat. If the presentation was extensive, as Milo was mentioning, we are more than happy to deep dive and have, let's say, further and follow-up conversation with your teams. We are happy to show you the software. We have several customized programs to make sure that you're able to touch the technology with hand and to see the value that potentially could bring with your, let's say, the developing process of your components. So we will share, of course, the recording. We will share the presentation, so you will also have our contacts. And in case, again, you would like to understand a bit more about the technology, the applicability to your component and your companies, we are more than happy to, of course, assist you.
He's asking, are you open also to co-design activities for VTS, or your core business is to develop the software at your side and sell the final product? Well, we can actually discuss about this. I should actually have more input about this to understand the context of this question. But what typically, I mean, our goal and our mission is actually to provide on the market a product, so a tool to enable actually the industry to use this kind of technology. Because we believe that can be a game changer, and there is a high barrier in order to use it due to the complexity, and therefore we want to reduce this barrier in order to spread the virtual sensing technology in the industry, and therefore our let's say our weapon is to offer the platform for doing this. Of course, we are more than happy to engage in collaboration, especially because in our team we don't have only software developer, but we have electrical machine design expert, we have control engineers, and in the past, but also today, we also offer support in this kind of collaborative scenario where, for example, our client has lackness of some of competencies, but still need in-house, but still need to reach the goal in terms of having this kind of real-time information. And we are more than happy, of course, to support and collaborate on this.
Thank you very much, everyone, for your participation, and we will, of course, keep you posted with product development and future use cases with our customers, so you can be up to date with how the technology is progressing.
Thank you for your participation.